Hello and welcome to lecture 35 on polar coordinates. So today we're going to be looking at a new coordinate system, and it's called the polar coordinate system. So let's write in the definition and also give you kind of an explanation of how we're going to create these coordinates. So the polar coordinate system, it chooses a point in the plane, and we're going to call that point the pole. But you might want to think of that as just the origin, and we're going to label that O. So let's go ahead and start drawing that over here. So I'm going to pick this point right here, and I'm going to label that O. Now what we do is we draw a ray horizontally, and we're going to create something called the polar axis. So from here, a ray just goes in one direction infinitely. It's like a half line, kind of. I'm going to draw this right here, and we're going to call this is the polar axis. So we're going to let P be any point in the plane. So we've distinguished this as the pole. This is our origin. We're going to pick another point P somewhere in the plane. So let's pick this one. And we're just going to say this is P, but we could choose any point. And we're going to assign to it the coordinates r, theta. Just like you would have like an x and a y, r and theta are going to give a description of where this point is. So what we're going to say is r is the distance. So if we go from here to here, r is going to be the distance from the pole to that point you've chosen. And you could think of it as the length of the segment OP. So r is basically how far away is this point from the pole, the straight line distance. Theta is the angle right here. So theta is the angle between this line segment OP and then the polar axis. So if you give me now the angle from the polar axis and the distance r, I can tell you where we are, like where that point is in the plane. So that's how we're going to describe points in this lesson. So let's go ahead and practice this by plotting a couple points, and then you'll get used to how this goes. So this is equal to some r theta. I think it's a good idea just to start with the theta. So 5 pi over 4, what I do is I go over here, and notice each of these circles, this is going to measure how far away I am from the pole. So here's the pole in the very middle, call that O. And each one of these, you count these by 1. This is the distance that you would use for r here. 5 pi over 4, that's in the third quadrant. So what I'm going to do is I'm going to go over here. This is my 5 pi over 4. So it would be in the third quadrant down here. So I know my point's going to be somewhere along this diagonal right here. And then r tells me I need to go 1 unit. So from the pole, I go 1 unit in the direction of 5 pi over 4. That's the angle I'm at. And then this right here, I'm going to label that A. So that's where the point A is. Let's take a look at this one. First, I'm going to go to the angle negative 2 pi over 3. So I'd start here, and I'd go clockwise, because it's a negative angle here. And if I go to negative 2 pi over 3, here's 1 pi over 3, and then here's 2 pi over 3. So it's negative 120 degrees this way. So here I'll label this negative 2 pi over 3, which is also known as 4 pi over 3, right? They're coterminal. But what I need to do from this angle is I need to count 2 for r. So we go 1, 2, just in the direction of negative 2 pi over 3. I'm going to label this one B. OK, and then for C, I have a negative r value, so I'm going to show you how to handle that. So write this somewhere in your notes. So negative r means plot on the opposite side of the pole. And I'll show you what I mean by that. Here's an equation too. You have negative r theta is the same thing as r theta plus pi. The plus pi means you rotate 180 degrees. So let me show you what it looks like on the graph now. First, we're going to go to 3 pi over 4. So that's in the second quadrant. So here's 3 pi over 4. So If I had a positive r value, I'd be going towards 3 pi over 4. However, because it's negative, what you do is instead of going this way, you flip 180 degrees on the other side. So instead of counting 1, 2, 3, like we've been doing, we're going to go backwards. 1, 2, 3. So it's like you're actually going towards 7 pi over 4 over here. So this would be 7 pi over 4. But we count 1, 2, 3 in reverse because it's negative. So then this would be point C. OK, so there's just some practice of plotting these polar coordinates. So this is how we're going to be identifying points using these two details here. So here's the important equations you need to know to be able to make conversions. So you're going to have to know these. So here's the situation. R is the distance from the pole O to P here. And then the distance in the horizontal direction is x. And we know that the distance in the vertical direction is y. So the equations would be, if you use your trigonometry, x is equal to r cosine theta. And then y is r sine theta. We know tangent is y over x because it's sine over cosine. And if you do the Pythagorean theorem, r squared is equal to the sum of the other two sides squared. So r squared is x squared plus y squared. So these four equations, I would just have these memorized, just so you can use them on command to make conversions if you need to. So this example says, plot the points and convert them to Cartesian coordinates. So right now we're given r's and thetas. I'm going to go ahead and plot them first. So here's the first one. You have 1 for r and pi for theta. So let's go over here. If you go to pi first, here's pi for the angle. It's on the left side over here. And we have to go a distance of 1. So from the origin right here, I'm going to count 1 to the left. So that right there is my point A, right there. So how would I convert that to Cartesian coordinates? Well, I need an x and a y value. So from these equations up here, I know x is r cosine theta. However, r is given as 1 and cosine is given as, or theta is given as pi. So this tells me cosine of pi is -1, so the x coordinate is going to be -1. And for the y, you have r sine theta from the formula up here. So again, r is 1. You have sine of pi, but that's just 0. So x, y, if you converted this, this would be -1, 0 for x, y. And when you're done, maybe take a second and look at that it makes sense, right? -1, 0 means you're to the left 1. So it matches up with my picture, right? I went to the left 1. So if I were to do this as like the grid I'm used to seeing, like this grid right here, like the x and the y here, it should be over 1 and then at 0, right? So it should match, right? Even if I am thinking about my graph paper like this, right? How we're used to thinking about it. OK, anyway, that was just an offhand comment. This is our next one. So let's go ahead and convert this one. X and y are the same formulas, so it's going to be r cosine theta and r sine theta. So let's plug it in. I get -2 cosine of 3 pi over 4, and then -2 sine of 3 pi over 4. So you're going to have to be pretty good at your unit circle stuff for this. I need to think, what is cosine of 3 pi over 4? Well, 3 pi over 4 is over here. And by over here, I mean in quadrant 2, right? So 3 pi over 4 would be negative square root of 2 over 2 for cosine. So I have -2 times negative square root of 2 over 2. So this tells me that we have root 2 for the x coordinate. And then let's go ahead and take a look at the y coordinate. So you have -2. But this time, since you're in the second quadrant, sine is positive. So we have -2 times positive root 2 over 2, which gives us a negative root 2. So converting the point, I get root 2, negative root 2. And that's now in an xy format, the Cartesian coordinates. Let's plot this point as well. So first, you'd start at 3 pi over 4. However, you have negative r, so you do what we did over here. Because you have negative r, you don't count that way towards 3 pi over 4. What you need to do is you need to count backwards. So we need to actually count 2 backwards. So instead of going this way, I would go 1, 2. And I'd be going towards 7 pi over 4. And then this is point B. So actually, point B is in quadrant 4. And if you look, I have a positive x, and I have a negative y, which if you looked at this grid again, a positive x and a negative y would put it in quadrant 4. So that all checks out. All right, so next, we're going to be taking a look at converting entire equations from polar to Cartesian and Cartesian to polar. And then last, we're going to start with our very first just 2 simple examples of drawing polar graphs. So I'll see you in just a moment for that. Welcome back. So for this first example, we're going to be taking a polar curve, and we're going to convert it to a Cartesian equation. So you may want to write a note to yourself that what we're doing here is we're taking the r thetas, that coordinate system, and we're converting it to x, y's. So that's the idea here. And you'll notice I left a couple things on the board from last time. These are critical. We have to use these formulas, so I have them still here. And then I have these graphs because I didn't want to redraw them again, so they'll come in handy later. OK, so r equals 2. We need to convert this, and we also need to use these equations over here. So my first thought is I have an equation for r squared. So I know from our list of 4 equations over there that r squared equals x squared plus y squared. So we know that. However, we also know that r is 2. And what I'm doing is, at the end, I want to just have x's and y's for my formula. So let's substitute in this 2. So what this tells me is that x squared plus y squared is 4. And that should be a familiar equation from algebra. What is this object right here? This is a circle. So I'm just going to do a quick sketch over here. So it's a circle. Its center is at 0, 0 because the x and y are not shifted. And its radius is 2. And there's no coincidence that this r is also 2. So the radius of this is 2. So from the center, I would count out 2 everywhere and hope I don't draw something that looks like an egg. Of course, I drew something that looks like an egg. But the center is at 0, 0, and the radius is 2. OK, so a lot of these examples, it's just you have to practice using these equations efficiently and ending up with something with just x's and y's when you're done. So this is the converted equation right there. Let's take a look at this. I have r equals 3 sine theta. Again, I would really like to make use of the fact that I know what r squared is. It's x squared plus y squared. However, I have this sine as well. So I do have a formula here that involves sine. It's r sine equals y. So one thing I can do to make use of both of these equations is I can first start by multiplying both sides by r. So you're going to get r squared is 3r sine theta. And now look what I can do. R squared again, if I use that, it's going to be x squared plus y squared. So that's what r squared is equal to based on the formula. R sine theta, I get to substitute in a y for that. So I have 3, and then I have this whole r sine theta is just y. OK, so I'm going to manipulate this a little bit more. Let's subtract the 3y over. I get x squared plus y squared minus 3y equals 0. I have both the x and the y variables are squared, and they both have the same coefficient. So this is going to be another circle. It's just going to be shifted a little bit. So what I'm going to do is I'm going to do completing the square. So you're probably happy that we did that earlier this semester, so you remember how to do that. We're going to take half of 3, and we're going to square that. So what I'm going to do is I'm going to add, and then half of 3 would be 3 over 2, and then I'd square it like this. And I'm going to do that to the right side of the equation as well. So it'll be 3 over 2, and I'm going to square it. Now, it doesn't matter that I didn't take negative 3, because when you square it, it's just going to be positive anyway. So then I get x squared plus y minus, and then this is 1.5 squared. So the number you use here when you complete the square, it's this half of b right here when I complete the square. So this is going to be y minus 1.5 squared, and this is going to be equal to 1.5 squared. So what is this? This is also a circle because I have x squared plus y squared equals r squared. However, there's a few differences here. So the center for this circle is going to be 0, comma, and then here's my minus k here. It's going to be 0, comma 1.5. And my radius is also 1.5. So if I do a little doodle over here, I need to make sure my center is at 1.5. So let's give myself 2 markings here. 1.5 right here. This is the center. And then I just have to count 1.5 in every direction. So that would be here, here. OK, and here comes another egg. Looks like that. So 1.5 for the radius, and 0, comma 1.5 for the center. So this is another circle. It's just been shifted. OK, and here's the last one. So r equals cosine theta, kind of weird. What I'm going to do is I'm going to rewrite this as r equals 1 over sine theta. And I'm going to multiply sine to both sides. So I get r sine theta is 1. Now wait a second. I just used this formula. R sine theta is y. So we have y equals 1. And you should remember this one from algebra. Y equals 1, what's that the equation of? It's nothing more than a horizontal line. So this is just a horizontal line at the coordinate 1 for the y variable. And that's it. So this one is much simpler looking than these other two. All right, now let's go in reverse. So I have the Cartesian equation, and I'm going to convert it now into its polar equation. So now my goal is to get these in terms of r and theta. So kind of the reverse of what we were doing before. Again, it all depends on knowing these formulas well. Our first one is x equals 3. That's a vertical line. So I know what the equation is going to look like. I need to convert this. So x is the same thing as r cosine theta. And that's equal to 3. Is there anything more I could do with this? Well, it's nice if you could solve it for r. So get the equation looking like r equals, like you have over here. R equals 2, r equals this, r equals that. So I'm going to solve this for r. And this tells me that r is 3. If you divide by cosine, it's the same thing as multiplying by secant. So r equals 3 secant gives you this vertical line. That makes sense because over here, remember, r cosecant, that also gave us a type of line. It gave us a horizontal line. So here's this first one converted. Let's move along. So here's x equals negative y squared. It's some kind of like parabola, if you think about that in the coordinate system we're used to. I'm going to directly plug in the formulas for x and y here. So x is r cosine theta equals, and then I'm going to have negative, and then y is r sine theta. I'm going to square it like that. From here, I'm going to go ahead and just simplify a little bit. I have r cosine theta is negative. That's last in the order of operations. I would take care of exponents first. I have r squared sine squared theta. I'm going to assume that r is not equal to 0. And I'll divide both sides by r. So what am I going to get for this? I'll get cosine theta is negative r sine squared theta. I'm going to solve this for r by doing two things. So the first thing I'm going to do is I'm going to divide by sine squared. So I'll have cosine theta divided by sine squared theta. Again, I'm going to assume that sine theta is not 0 in this case. So I'm going to assume I can do that. And then I'll multiply by the negative. So I'll get r equals negative cosine over sine times 1 over sine. And if I want to make that look just a little better, I'll say r is cosine over sine. That's cotangent, so negative cotangent. And 1 over sine is cosecant. So I've converted this parabola into r equals negative cotangent times cosecant theta. And my goal has been reached here because I solved it for r. And everything in here is r's and thetas. There's no more x's and y's anymore. Let's take a look at this last one. The cleverest way to do it is if you see x squared y squared, you can immediately replace that with r squared by equation 4 here. So you have r squared is 2c, and what is x? X is r cosine theta. And then the last thing we need to do to solve for r is all I'm going to do is, assuming r is not 0, I'll divide both sides by r. I'll get r equals 2c times cosine theta. I'll make that very clear that this is cosine theta and this is a constant c. So this c was just some constant. I'd like to start graphing polar equations. We're going to devote the entirety of the next lecture to do just that. But here I'm going to just show you 2 really basic examples to get us started. And then I'm going to have a whole video where I show you like all the different types of polar graphs and the things I want you to know. But let's just start with this first one. So here theta is pi over 3. So that's the equation. What this means right here, and I'll write it right here, it means that we need all points such that the angle, you could say it with the polar axis, is pi over 3. So I could list a bunch of points that do that on this graph. So we could have 1 pi over 3, 2 pi over 3, 0 pi over 3. Any chance you can put pi over 3 as the theta value for r comma theta, it's allowed. But also, remember, r can be negative. So it could be like -1 pi over 3, -2. You get the point, right? -2 pi over 3. What does that look like on the graph? Well, here's 0 pi over 3. And pi over 3 is right here. So you're going to walk towards pi over 3. So here's 1 pi over 3, 2 pi over 3, 3 pi over 3. It's all of these points. But also, you could go backwards. At pi over 3, you can go -1, so walk backwards. So what you end up getting for an equation that's just theta equals some angle here is you get a line. And it's just the line through that angle. So this is one of the more simple polar graphs. So I can introduce that right now. So that's how you should think about that one. This next one is a little more complicated. But I have another graph right here. So what you could do is you could try pausing the video, fill this out for me, practice your unit circle stuff. And when I come back, it's going to be magically filled out. OK? I'll see you in a second. All right, so now I have all of the table filled out. Take a second in your notes to check that you got what I got. If not, make corrections. The unit circle stuff should be really, really fresh in your mind moving forward for this lecture and the next few. So for the first one, when I plugged in 0, I got 2. So this gives you the coordinate 2 for r and 0 for theta. So you could think about plotting the point 2, 0 over here. So that's 0 is the angle. So it's right here, the horizontal. And you have 2. The next one would be √3 and then pi over 6. So, √3 pi over 6. So here's the angle pi over 6. √3, it's about like 1.7. So what I'm going to do is I'm going to draw something right here. And then here at pi over 4, that's the 45 degrees, it's √2. So that's about 1.4. So I'm just going to, I'll write some of these in for you, 1.7. So it's going to be a little more towards the pole. So it'll be somewhere like here. Here we have pi over 3, 1. So it's continuing to get closer and closer to the pole. And now it's at 1. So it's on the first circle here. Here's pi over 3. It's on the circle now. Pi over 2, the 90 degrees, it goes back into 0. So it hasn't moved at all. So it's here. And then at 2 pi over 3, it goes to -1. So 2 pi over 3 is over here. So this is 2 pi over 3 at 120. However, you get -1 when you plug in 2 pi over 3. So what happens is, instead of going 1 this way, it goes back around here. And now you also have to think about going in order, like sweeping through this whole path in order. You start at 0, which we started here, and you follow this along here. And then you have a symmetric thing. If you keep plotting even more points, you have a symmetric thing happen right here. So what kind of equation did we get when we took our time and mapped this all out? Well, this is actually a circle. So graphs that look like this, where you have r equals a sine or a cosine, those are circles. And a gives you the diameter for that circle. So we're going to talk about that in much more detail later. I'm going to give you a family of these graphs and a bunch of other different cool-looking polar graphs. But that's all I want to do now for this lesson. As always, please reach out to me if you have any questions, and I will see you in the next video. Have a nice day.